Great. Welcome everybody for our usual weekly seminar. And it's a great pleasure to have today Hong Liu from IBS Korea. And he will talk about multipartite sparsification and colored Turan problems. Please, Hong.
Thanks, Benny, for the invitation. So yeah, I will be talking about actually a work in progress. So the paper is not on archive yet, but we hope to put it on archive soon. Let me start with a social choice problem, which seems quite natural. So the social choice problem. So what is this question? We have a country. So a country which has, let's say, capital N towns. We would like to form a council of towns, and the goal is to form a council of towns. What are the requirements? Well, first of all, each town, if they get represented, they may send a delegation of bounding number of members. So each town may send a bounded, let me be specific, let's say some number S of epsilon, bounding number of people. This is natural because we don't want each town to send unbounded number of representatives. And the second thing is there's of course, in human relation, there's conflict of interest. So between every pair, let me draw a picture. We have these are the towns, right? The V1, V2, Vn, these are the towns. Now between every pair of towns, there are people that hate each other. But the proportion is not so big. We know that the at most D proportion fraction of pairs from every pair of towns, they have conflict of interest. So each pair of towns has at most D fraction of people with conflict of interest. Now, naturally, the council we want to form, the people they cannot have too many pair of people in conflict of interest. So we are willing to pay an additive epsilon cost, meaning the eventual council we're going to form, if two towns get represented, then the fraction of pairs of people from these two towns that get represented is that has conflict of interest is at most D plus epsilon. So we want for any pair of represented towns, I'll apologize for my handwriting. Let me write slower maybe. Represented towns at most D plus epsilon fraction of people have conflict of interest. Right. Now another natural requirement is we would like this council to be multipolar because we don't want just having one town there dictating everything. So another requirement, want the council to be multipolar. So what does it mean? Specifically, we would like to have as many towns represented as possible. So want, i.e., to have as many towns represented as possible. Okay. So with all this requirement in mind, the question comes, if we have the question, let's say we have a prescribed number of towns, we want M to be the number of towns represented. Is it possible to have any prescribed number M of towns represented, given that each town can only send a bounding number of people, having the requirement that they cannot increase the fraction of pairs of people having conflict of interest? So the emphasis here is that this is not an easy problem. In fact, we can represent it as a multipartite graph, and then you do this random sampling. But the problem is, given that each town can only send bounding number of people, to have as many towns as possible, like M towns, and while only increasing the fraction of conflict of interest people by additive epsilon, then usually a naive Chernoff union bound will require S to be also depending on M. But here our requirement is S must be independent of M. Okay. So given any M, is it possible? Is the question clear? So feel free to interrupt me anytime if any
Throughout,
questions.
you're assuming that capital N is much, much larger than M. And all
Capital
the
N
other
is much, much larger. That's right. Yes. So a priori, this is not clear at all. Not even it's not even clear that if it's true. But I can tell you the answer. At the end, we will see that this is possible, provided, as Alexa said, we just need to require N is sufficiently large compared to M. Then we can indeed do this. So the moral of the story.
I have a question. So this looks like very much what people do in property testing, right? You want a sketch of your graph, no?
Right. It's like a coarse version of our graph, a low resolution version of the graph.
So didn't people study similar question when they study property testing? Right? Also there they want a small coarse version of the original graph, no? How this is different?
I don't know, but I definitely will look it up. So this is still work in progress. We are still looking for more applications of this lemma, this result that we have. So maybe this, as you said, property testing, right? Maybe I will look into we can look into it. Yeah. What did you say? Property testing and the sketch, low sketch?
In property testing, right, it's usually they have a big graph and they want to see if it's close to have certain properties. And they're usually sampling or doing something on a fixed size subgraph. And from that, they want to get this type of thing. So it might be it's related to the problem they looked at, right?
Right.
Because that's what they're doing there.
Okay, yeah. Thanks. So, all right. So let's keep this this question in mind, and let's start with just to make sure everyone on the same page. The main application we will have is a Turan type problem. So let's go quickly through some basics of this Turan business. Okay. So this is Turan 101. Okay. So here's the background. First of all, we need to explain what is the graph being H-free. This just means it does not contain H is a subgraph. And that means we don't have an injective map from V of H to V of G, preserving the adjacency. Okay, no problem. And we can define this a very important parameter, the extremal number of graph H, to be the maximum number of edges in the graph G, such that it has n vertices. So that's the first parameter n, and the graph is H3. Okay, so for example, if we have one triangle free, the best we can do, as we most of us know, that the Mantel theorem says complete bipartite graph is the best, having n squared over 4 edges. So after a long sequence of work, starting from Mantel, this is 1907, then Turan greatly generalized it to all cliques, 1941. Then later, we're going to see Erdős-Storm proving, which can be considered as the fundamental result in extremal graph theory, that the extremal number is asymptotically determined by the chromatic number of forbidden graph. So let's normalize everything. Let's talk about the Turan density. To be the extremal number of our function, of our graph H, normalized by total number of pairs. So this is the fraction of edges that can present in an H3 graph, the maximum fraction. And this limit exists by just some averaging monotone arguments. So, right. And this Erdős-Storm theorem is saying that the Turan density is 1 minus 1 over chi of H minus 1. So this determines the Turan density for all non-bipartite graphs. For bipartite graphs, it's a difficult problem, which we're not going to talk about today. Now, let's introduce this variant, the multipartite version, that was already suggested as early as in the 70s by Bollobas. So, multipartite Turan. Okay, so what is this doing? So this is suggested by Bollobas in the late 70s. In particular, it's in his book, this extremal graph theory book. Now, let's just consider a baby case. Still embedding triangle, consider triangle free graph, but in 3-partite graphs. So, but as we will see, I call this baby case is already non-trivial. So now we consider a 3-partite graph. This is our host graph G. And now the condition is not the number of edges, but the pairwise density, a minimum on it. So we know that between every pair, the density is at least D. Okay. Pairwise density, at least D. Then what will be the natural multipartite problem? What's the minimum D that when each class is large enough, we can always guarantee a triangle in our graph? Okay, so the multipartite problem is, what's the min D that will force a triangle? This is the 3-partite question. So let's try to work on this one for a little bit to warm up. What will be a natural guess? Well, here's a natural guess. And we will see that this is indeed a natural guess because it will appear later. It will be useful later. So a natural guess is 1/2 density, just as we see in the usual Turan. And how we can realize this, we can draw like these are the 3 parts. And then we cut the parts into 2 parts, equal weight. And we just have edges like this. And just to be prettier, let me use a different color. So the edges won't tangle together, okay? And how many edges? Every vertex is the same weight, 1/2. So how many edges going across between different parts? There are exactly 4 edges between every pair of parts. So the density is 1/2, this one. And easy to check that this is triangle free. So density 1/2, triangle free. In 2006, Boundy, Shen, Thomas, and Thomason resolved this three-partite problem, proving that actually we can do better than 1/2, and the correct answer is the golden ratio. So the answer, this is the guess versus the answer, is the golden ratio. Roughly 0.618. And how to realize this? The extremal graph is also simple. Let me draw it this way. Just a C5. Okay, it's a C5. And you adjust the weight of vertices down here, we can make sure that the density going across every pair is this golden ratio 0.618. This, okay, very, very satisfying answer and a slightly surprising answer also. So this is by Boundy, Shen, Thomas, and Thomason. Maybe there's no double S here. Single S. Oh, it is double S. Sorry. Okay, 2020 is almost 20 years ago. Now, they further prove that if you, this is only 3 parts, right? Now, if you let the number of parts gets larger, k parts, and again, the requirement is we have pairwise density d between every pair. Natural question is, how does this density, that force triangle, changing? And they managed to prove that eventually as k goes to infinity, the limiting density approach to the usual Turan density 1/2 for triangle. So this BSTT, they prove that, and they prove, in fact, this is true for any graph, forbidden graph H. So for any forbidden graph H, as k goes to infinity, which is, I will always use k for the number of parts, then this k-partite Turan density, I didn't define it formally, but hopefully we know what it means. Turan density for H, as k equals to infinity, approach to the usual 1 minus 1 over chi of H minus 1. Okay, that's quite nice. In the same paper,
I
yes.
have a question. So one can look on more general question where you allow this D to be different and you just take sum. Is it a very different question?
Right. So in their original paper, they actually work on this some variants of these. I think it's slightly different. One can work out this whole profile, as you said, right? What are the alpha, beta, gamma, so that and plot out this region. But I don't believe this question is systematically studied for general graph. I'm not sure. Yeah. Right. So here it's like the minimum one, right? Okay. In the same paper, they conjectured that this limit can never be reached, this limiting density. What does it mean never be reached? That means whenever you take finite number of parts k, then the Turan density is always strictly larger than this. Okay, so they conjecture, oh, I should make this larger. Okay, they conjecture that this limits 1 minus 1 over chi of they actually just consider complete graph. Okay, let me write it like this way. They conjecture that for complete graph, it can never be reached. Cannot be reached. by finite number of parts, K. This is proved false a couple of years later by Fender, who show in particular for triangles, once you have 13 parts or above, then density is 1/2. So it can be exactly reached. So he actually proved for any clique or cliques, KR, some finite K, we can get exactly this 1 minus 1 over R minus 1. Okay. And in the same paper, Fender conjectured that this is also true for general graph. The limiting density can be reached by finite number of parts. So he conjectured that true also for all H. This was proved some 10 years ago by Narine, disproved, and Turan trained that's false. They actually characterize all graph H, for which after finite number of parts, the limiting density 1 minus chi of H minus 1, 1 over that can be reached, and all those that cannot be reached. These are eventually, they characterize all H. Okay, it's not the focus on our talk. Let me be a little bit brave. Essentially, they prove that if in optimal coloring of H between two color class, you see only a matching, then those are the ones after finite number of parts you can reach it. Otherwise, no. Okay, so what we're proposing, which is linked to the social choice problem we see at the beginning, is a more general setting of a colored color setting. So let me just say briefly for now, and I'll define things more formally. We can view this multipartite as a colored setting where we embed this graph H or KR, where this H or KR come with a coloring, a rainbow coloring, which requires each vertex to go to different parts of the host graph G. But we can give any proper coloring of H and then embed it in G as requiring that vertices that get same color in this proper coloring get mapped to the same parts of G, right? So let me write down this very natural definition of colored graph homomorphism. So more general colored setting that generalize this multipartite setting. First of all, let's see this definition of colored homomorphism. This is, as you might guess, just a homomorphism between two colored graph where also the colors get preserved. Meaning, if two vertices, they have the same color before, in the image, it's the same. Let me write it down formally. So we have F and G, they are, when I say color, it's always vertex colored graph. And a colored homomorphism from F to G, it's a graph homomorphism preserving adjacency. And if if two vertices have the same color in G, if and only if the pre-image have the same color in F. Okay, very natural definition. Right, so let me first maybe give you a little bit hand-waving, saying some motivation of this colored homomorphism. Why this is interesting? Well, first of all, it's a natural thing to define with actual color preserving property. Second of all, in many extremal problems like embedding graphs, embedding spanning graphs in particular, sometimes when we apply regularity lemma, some vertex they have a designated place to go to in some parts, and this can be described by this colored homomorphism, right? So, for example, in some embedding problem. Some vertices have designated place to go to. Okay, let me just be brave. And another thing is sort of like testing this non-repetitive coloring. Non-repetitive coloring just means that it's a coloring such that on any path, we don't see a square, meaning this ABC pattern that get repeats twice. This is something introduced a while ago by, let me see the people. I will not write it down. Let me just mention by Alon Jechuk, Howushchuk, and Riordan. And how is it related to this? Well, if we look at all square paths, this means all the paths that get colored by even path that get colored by squares, like this 1, 2, 3, 1, 2, 3. If we can test whether you contain such colored path as subgraph, we can see whether this is a non-repetitive coloring. Okay. Now, let's see some examples of, I need to also define, and let me introduce another definition called K-colored, our host graph, K-colored D-dense graph. This is just this definition, let's give a formal name. It just means this is a K vertex colored graph where each class is now empty. And between every pair of class colors, densities at least D. Just this K-partite thing. Let me phrase it in the color language. Okay, this 1, 2, 3 to K, da da da. Density at least D. Just give a formal name. Now let's introduce see an example of a very important colored graph, the K-half graph. Let's look at this one. What is the usual half graph? We have two rows of vertices, AI, BI, AK, B1, B2, BK. And vertices on top is linked to the bottom if only if the index is strictly smaller. So AI is like this and dot 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 linked to all the right. AI always go to the right. Okay, like this. The last guy only linked to this guy. Is the definition clear? Please let me know if anything's not clear. Now, this is an important graph, linked to also quantitative bounds on regularity lemmas, other things. Usual way of people viewing it is a bipartite graph, where we view rows as parts. But now we're going to view it as a K-partite graph, where we look at column-wise. So now we're going to look at column-wise. So each column now is a color class. Okay, we K-colored this. Now, what's the density of this K-color graph? This K-color graph is 1/4 dense, right? This is 1/4 dense. And this 1/4 number is also an important number because between every pair of class, the only edge we're going to see is this AI to BJ, the smaller one on top to larger one on the bottom. And this is one out of all possible 4 edges. It's 1/4. There is another reason why viewing things columnly is more natural, because this is locally symmetric. They locally look the same. If you take any T parts, T column, they locally look exactly the same. This is another comment, okay? Locally the same when viewing things column-wise. Good. Now we can introduce this colored Turan density definition. We define, we have to first give a forbidden graph. This is F, for any F. For any K, which is at least the chromatin, K is a colored graph. So we first give a colored F, and then we give a K, which is at least the number of colors in F, so we can embed it. Now, the colored Turan density of F, given a number of colors K, is the infinite D, such that for any K colored D dense graph G, it contains F as a subgraph, as a colored subgraph. Well, actually, contains F as a homomorphism from F to G. As a subgraph, we need to be injective. So all we need to do is to make sure that each color class of G is large enough, but this is technicality. So I'm hiding the fact that each color class of G is large. It's not going to affect anything. So this is the color density. And now, as I would like to say, we want to study the case when K goes to infinity. So the infinite partite Turan problem. So we're going to define the color density of F to be the limit of this when K goes to infinity. All right, let's see some example. And we will see that things start to get a little bit strange in this more general colored setting. So let's start with the thing that we have seen before. So examples. The first example is for F with rainbow coloring. This is the thing we've just talked about. Rainbow coloring means every vertex of F gets a different color. This just means they cannot be mapped to the same part of this K-color D-dense graph. So it's the same as the multipartite Bollobas version. Before, and by this boundary Shen Thomason's result, we know that when number of parts goes to infinity, they prove that if you embed F, every vertex F in different parts, this rainbow setting, the limiting density is the usual Turan density. And we know in this setting, color of F equals to 1 minus 1 over chi of F minus 1. Okay. Now let me prove you, let's see some simple proofs. The second example is when F comes with the optimal coloring, which is also a natural one. So 2, F with an optimal R equal to chi of F, let's say, coloring. Okay, so F is optimally colored. I want to prove that, convince you that this is, again, 1 minus 1 over R minus 1. First of all, the lower bound is easy. Let's see a lower bound. This lower bound is true for any colored F, not just for optimal coloring. Okay. Lower bound. So what will be a lower bound? If we know this lower bound is true no matter the coloring of F. So for any F, let me write it independently. If chi of f is R, then for any coloring of f, chi co of f is at least 1 minus 1 over R. Here's the construction. So what do we need to do? Right? Infinite number of parts. So as many parts as we want. This is first parts. We want to have between every pair density at least this much. All we need to do is to put a complete bipartite graph on R minus 1 vertices on each part with a perfect matching removed. So that means we're going to cut everything into R minus 1 parts. 2, R minus 1. Now I put all edges sorry, not the same index with the perfect matching removed. Okay, let me use red for non-edges. So between same row, there's no edge. All right. So the density of this is easy to check. Let's check it. The density. What's the between every pair? They look the same, right? Just repeat. The density is what we have R minus 1 square with R minus 1 edges removed. Then we need to divide by total number of pairs, which is R minus 1 square. So this is 1 minus 1 over R minus 1. Why this does not host any F with any coloring? This is also easy, simply because this graph, host graph itself, is R minus 1 colorable. Each row is an independent set. So the host graph G itself has chromatic number R minus 1, whereas F has chromatic number R. Okay, that's it. How do we prove? Any question? How do we prove that if the coloring is optimal, then this is a matching upper bound? This is also not hard. So let's look at upper bound. Okay. This upper bound is because now we need to prove that optimally colored F and most 1 minus this. Well, let's look at a K-colored, a graph G that's K-colored and D-dense. What's its Lagrangian? Lagrangian is at least, easy to compute, K minus 1 over K times D, right? Because it's K-partite. By just adjusting each parts to equal size, we get this Lagrangian lower bound times the density D between every pair. Now, this guy can be made to be...
Sorry, can you remind us what the Lagrangian of the graph is?
The Lagrangian of graph is just you put weights on the vertices, which sum up to 1, and then you compute this weighted number of edges in the graph. Meaning that if ij is adjacent, then the count to the contribution to Lagrangian is xi times xj.
And I look to maximize this.
And you want to maximize this, yes. Lagrangian is the maximum of that over this whole simplex.
Okay, thanks.
Okay, so, thanks. Yeah, please ask me for this question. So if D is strictly larger than, so we want to prove upper bound, right? If D is strictly larger than this upper bound, then we can take K large enough so that this is still larger than this number, right? There's a gap. So take K very large, we are still larger than this. Then we are done. We can by the clique result, the clique rainbow result, we know there's KR in our graph G as a colored graph, right? Then you just embed this optimally colored F into this KR. I mean, in the homomorphism sense, but if you pull it up, it's a subgraph. So that's a sketch of the proof, not very hard. Now let me show you something strange that's happening. Let's look some bipartite graph, remember, Turan density is 0. But in the infinite multipartite setting, colored setting, it could be strictly positive. So strange things could happen. Let's look at P5 with this coloring. I use 3 colors. It's a proper coloring. 1, 2, 3, 1, 2. Okay. Now I want to convince you that for this particular P5, this is at least 1/4 is positive. So how do we prove that? Remember this half graph that we mentioned. Remember this K half graph. Density is 1/4. All we need to prove is that this color copy of P5 does not embed into half graphs. So let's recall, you have half graph that look like this. Every guy goes to large index at the bottom. So in the first 3 parts, it looks like this, right? It's enough to just look at only 3 parts. Why? As we mentioned, this K graph, if you view it columnly, locally they all look the same among any 3 parts. And we know that we are 3 coloring this P5. So only 3 parts we can embed these vertices to, right? Same color class, same color vertices must go to the same class. Now, the key thing to observe, let me just be hand waving because I'm running a little bit late. Why this does not embed to K half graph? Look at this guy, this coloring. This coloring has the property that every color has a vertex like this one adjacent to both other color. So this vertex 1 adjacent to 2 and 3 color. This color 3 adjacent to both 1 and 2 color. This color 2 adjacent to both 3 and 1 color. Okay. Now suppose we embed this coloring, color P5, suppose we can embed it, and suppose color 2 goes here, color 1 goes here, color 3 goes there. Other cases are symmetric. What's the problem? The problem is where we can embed this color 1 vertex. Where we can embed this guy. This color 1 vertex must be adjacent to some color 2 and 3. If it is embedded up here, it only sends edges to the right. So you only see the color 3. If you embed down here, it only sends edge to the left. So you only see color 2. They only see 1 color. This gives you the lower bound 1/4. Okay, so things could be strange. And how strange it can be for bipartite graphs, actually it can go, for bipartite graph F, it can go anywhere between 0 and 1/2, arbitrarily close to 1/2. Let me just stop here because I want to mention more interesting things. So now I need to say something a little bit more hand waving. The difference between finite number of parts and infinite number of parts, there's a fundamental difference. So difference between bounded number of parts and infinite number of parts. The difference is symmetrization technique. What does it mean? Let me just be hand waving. Suppose we only have 3 parts, and this is a 3-part, some D-dense graph, right? In our language, it's 3-colored D-dense graph. Why bounding number of parts is easy, no matter what color graph you forbidden? Well, because of symmetrization. If you look at vertices here, they only have 2 constraints going here, here. That means if you ever have 3 types of different vertices, you have 1 degree of freedom to move weights like Moskine-Strauss, so that you satisfy that both these 2 constraints, you don't go in the bad direction. In other words, you may assume that each color class only contains 2 types of different vertices. In general, if you have k-colored, k parts. Each part contains only at most k minus 1 different type of vertices. Okay, let me not go more on this. But for infinite, this is not possible. If you have infinite number of parts, you cannot bound the number of different type of vertices inside each part. So for infinite number of parts, that's what we do. Study this colored density. We have to do something different. This is where, so for infinite number of parts, our idea consists of two parts. One part is this multipartite sparsification, which I want to mention it, which then help us to reduce this infinite multipartite colored Turan problem to a directed Turan problem. And for directed Turan problem in the 80s, Shumanovich, Erdős, and there's some other group of people. Yeah, there's a Brown, Schorsch, maybe. There's a systematic study. So the key thing I want to mention now is this sparsification. So I have like 8 minutes, right, Benny? Okay, so maybe let me mention very briefly how we can connect to directed Turan problem. Then I mention this at the end, the sparsification. The directed Turan problem is that using this, we can show, let me show you what's the connection. Again, look at this colored, for a directed graph, D, we can define a certain blow up. So the D comes with some direction. If I is directed to, let's say, k-partite blow up, how do we define this k-partite blow up? We just draw k copies of D. Okay, you put k copies column in the column wise. But this indices is important, 1 to k. From small index to large index, whenever you have a vertex, you have an arc from U to V, then the corresponding vertex U sends an edge to V. Okay, in this sort of directed way, but we forget about direction now. Direction is encoded by this index I to J. Example, the bad things to say example. What's the k-half graph? We keep seeing it. This is actually, you look at a graph, just a 2-vertex graph, directed graph with a single edge. You blow it up by k. This is the k graph. Let's see. You draw these copies of directed graph, right? Which has 2 vertices. This is the AI to BI. You have A row and B row. And between I and J, smaller index, you only go from AI to BJ. That's precisely the blow up of this order graph. And in short, basically through sparsification, we can show that this, for any graph F, even for family, in the colored Turan density, this is a theorem, via sparsification, the colored Turan density of F is actually linked to the usual Turan density of some family of directed graph coming from F. Where this directed graph family is a finite family that can be explicitly defined based on this coloring of F. Okay, so this part I won't have time to talk about it. Let me talk about this sparsification in the remaining time. I will just write down the lemma and then tell you a sketch of a proof. So here's the sparsification. For any epsilon, there exists S of epsilon such that for any M, there exists N depend only on epsilon and M such that for any n large, the following holds. So for any n-colored D-dense graph, on, let's say, V1, V2 to Vn classes. So you have this. We can find there exists a sub-index number of parts of size m. You can find m parts, and Si, a set of vertices in each Vi, where Si is of size S, depending only on epsilon, such that between any Si, Sj, the density is at least D minus epsilon for any ij in I. That's precisely, if you think a little bit, the social choice problem we said in the beginning, where the conflict is measured by the complement of this graph. Anyway, now let's just purely look at this lemma.
Oh, so the parts have the same size?
The class, yeah, let's say same size and sufficiently large, say. Let's make things simple, yeah. So, okay, what's the merit? The important thing is S is independent of M. Okay. Right. Let me draw a picture. This means that we can find M number of parts so that between every part, we preserve the pairwise density up to epsilon error. And the size of this is bounded as epsilon. Why this is surprising? Let's think a little bit. If you use Chernoff to preserve this density up to epsilon, and you need to preserve it for all M choose 2 pairs, then we will need S to be like some function of epsilon times log M, sort of, right? You need to sample log M vertices or something like that to make sure that all M parts. But here, there's no log M. So this is a rare new instance of beating the naive union bound. There are very limited number of examples of beating union bound, the random union bound. For example, this partial coloring, right, by Spencer in studying this discrepancy problem, you can beat the union bound. The very limited handful of examples. So here's another example. So now let me give a sketch, at least in the remaining 1 minute, 2 minutes, I give you some idea how to prove this. So the thing is, we cannot use union bound. If you just bound the failing probability and apply union bound, you would have some log M appearing in the size. The idea is the problem here is that if you sample things once, sample this, we will do random sampling. But there's too many dependence, pairwise dependency between all these sample vertices. We're going to sample things in rounds. And then we're going to sample things in a multipartite way to reduce dependency. That's the idea. So very hand-wavingly, let me give you the idea. Here I will use these rows for this number of parts. So each row is this part, okay? So we have the parts living here. And we're going to sample in multi rounds. In each round, we're going to sample some small set of vertices. Okay. And at the end, you're going to take the union of these. This will be our SI. You take all these sample vertices together, that will be this guy. What's the invariance we want to keep? Now I'm running out of time. The key idea is that when we sample these vertices, the original requirement is that we need to preserve the density up to epsilon error between all these pairs, right? Now instead, what we require is you only need to preserve density to the mother set, to all this previous set, to the whole set, and that's it for the first round. just to the mother set, not between themselves. So that reduces dependency. In the second round, goes always to the mother set. You preserve up to d minus epsilon. That's doable. And also you preserve to the previous selected rounds in other parts. Only in the previous round. So same. For example, now we're in the fourth round. You only go to the previous round. For all previous round, you preserve it. Okay? Intuitively, that would kill all the dependence for pairs of sets selected in the same round. And this does not lose too much because eventually when we take the union, we have all control on the cross pair density. The same pair is negligible proportion, so you can still maintain the cross density. Okay, that's the first thing. Second thing, I'm hiding something that's actually the key idea here that makes everything work. We have to use Ramsey argument every time shrinking this index n, passing to a sub-index in each round to make things work. Because to make sure that you have the right density to the previous selected round, this is not true that without shrinking the indices. So we have to use some sort of Ramsey argument to maintain these. Okay, let me maybe just stop here. Thank you.
Great. Thank you very much, Hong. So questions?
So I had one quick question, which is about one of the easy proof that you said that maybe I missed. So you were explaining us how if the coloring of F is optimal in our colors, then you can get an upper bound for this colored version of Turan density. And then you concluded the proof by saying that KR embeds into G in a colored fashion. But so how does that give you F in the end? Because F may have several vertices of the same color. I maybe just didn't hear what you said back then.
Right. So it's the same as saying in the usual Turan business, the Turan density of a graph and its blow up are the same. Because if you just think about embedding injectively or not injectively, it's the same when the graph is large enough. This is also true in the multipartite sense, right? If we can embed KR, then we have a colored homomorphism from F to G, right? With the optimal colored F, color homomorphism. Each color class mapped to each vertex of KR. And now you just imagine you blow things up in this usual way. Well, you have to write things down more formally. It's not like
so you do some kind of regularity argument to
not regularity. You just blow up and take the limits. You can show that you can make this embedding injective as a colored graph as long as each color class of G is large enough. Yeah, you don't need regularity. Yeah.
Sure. Thanks.
Yeah. So I have a question. So the number n is a function. The number n is a function of m. Is exponential, right? So how big your n you need?
You are saying
This
guy,
n.
right? This guy?
Yeah.
It's horrible because we have to use hypergraph Ramsey in each one of these rounds, in many rounds. So this is like many rounds Ramsey compound together. It's bad. Yeah. But really, the thing I want to emphasize is that this sort of like a decoupling, reduced dependency, we can do better than naive union bound. This is something I find it quite nice. Yeah.
Let's see.
But yeah, for the audience, we are still looking for application of this. But so far, maybe this property testing we can look. If you see some other places, please let me know. Yeah, email me.
Let's see. More questions? If not, we can stop recording.